Sandra Liu is an MIT PhD graduate who designs and builds robots inspired by human hands. To do this, Sandra uses soft, squishy materials and special rainbow light cameras to help robots grip and identify the objects they encounter, from Rubik's Cubes to cups. Let's go meet Sandra!
Hello, everyone. Thank you so much, Fatima, for the lovely introduction. And thank you guys so much for all being here. I hope you're super excited to talk about squishy rainbow robots today. But actually, before we do that, I'm going to do a quick introduction about myself. So hi, everyone. My name is Sandra. It's super nice to meet you guys all online. And for a lot of background, I originally was at Caltech before, and then I just finished doing my PhD at MIT in mechanical engineering. So you can see me here with working a big machine so that I can actually make something that I want to build. And some other things I like to do in my spare time is I'm huge on doing jigsaw puzzles. I love making prank cakes. So if you actually squint really closely, this might be made out of cucumber and salad greens. I'm also really into photography. I really like black and white film photography. And my favorite part is actually standing in something called a dark room and just spending hours in the dark using chemicals to develop the pictures I take. I also play the violin. And so if you squint at this sort of bad resolution photo, you can actually see me there. And okay, so now that we've got the introductions out of the way, you might be wondering, what does squishy mean in this kind of sense? What is a rainbow robot? But actually, before we even get into that, let's talk a little bit about why I got into robotics in the first place. And so put simply, I think robots are super cool. So this is a video from Boston Dynamics, and it's a bunch of their spot sort of dog-like robots dancing together to a BTS song. And another part of robotics that really drew me to it was that that robots are actually able to help people. And so one of these things is perhaps you'll recognize this picture, which is of a Roomba or a robot vacuum that is prevalent in a lot of people's households. Also, a lot of robotic arms are in industry and they can help a lot of people, for example, passing cups around. And another thing that really got me excited about robotics was the idea of prosthetic hands. So a lot of people who can't use their hands or don't have function of hands actually rely on prosthetic robotic hands to be able to do a lot of their day-to-day tasks. And the human hand is actually very fascinating. And so the idea of using a robot to replicate that human hand was something that really excited me and got me into doing robotics in the first place. Okay, but you might ask, wait a minute, Sandra. All of these robots aren't actually squishy at all. In fact, probably the squishiest thing in this slide is the cat, which is most definitely not a robot. And so what are squishy robots? And in our field, we like to call them soft robots, actually. And so there are a lot of different things. One of the things that's most key to them is that instead of using these rigid metal parts to build them, we actually use soft plastic or rubber parts. And this allows them to do a lot of things. They can squeeze through tight spaces because they're very soft and compliant. We can also build them into robotic fish so that they can swim around in the ocean. And my favorite part, of course, is that we can make them into soft robotic hands that are capable of interacting very safely with a lot of things. So here we actually see it picking up a live crab very delicately and gently without harming it. And now, of course, because just building a soft robotic hand isn't enough, a lot of my PhD was actually trying to figure out how can we actually make this robot better. And one of the things that my lab does rather, is we incorporate touch sensing and we think about how we can add touch to these soft robotic hands. And so the idea of touch is actually something that we really underestimate how important it is. But one example that I like using is imagine that you're like this person and you're reaching into a grocery bag. Now, inside this grocery bag, there could be a lot of different things. And maybe it's dark outside, so you can't see inside the bag. Maybe there's so many things inside that it's hard to figure out what you're actually reaching. Or maybe your eyes are just simply closed and you can't see what's inside. So what can you determine with this idea of touch? And there are a couple of things. One example is you can tell just from tactile sensing, or touch sensing rather, whether you're grabbing a banana or a pineapple. Because, well, a banana will feel like a banana, and a pineapple will probably be very sharp, and you can feel that with your fingers. You can tell if a fruit is ripe. So if I grab, for example, an avocado, I can tell really quickly whether it's soft or whether it's firm and whether or not I can eat it at that point. And perhaps a little more of a subtle point is you can determine if something is too slippery to hold. So if you grab it and it feels slimy, then you know that you have to actually grab it with more force or else it might fall out of your hands. So one touch sensor that my lab uses a lot of is something called the gel set. And it looks a little wonky, but let's walk through how exactly it works. The idea is quite simple, actually. We take this camera and we sneak it into the bottom of it, and the camera takes a look at this silicone rubber pad on top. And if we use a microscope to look closely at the silicone rubber pad, we actually see that there's a lot of these little tiny pieces of what we like to call aluminum cornflakes, which is so named after an American cereal that some of you guys might be familiar with. And the whole point of aluminum cornflakes is that we have a lot of different sized pieces. And this means that when we shine light onto it, the pieces behave differently under light. So some pieces will have perfect reflectance, while other pieces will perfectly scatter the light around. And this means that if we take the silicone piece and we shine red, green, and blue lights or LEDs onto it, and we put a spherical contact on top, we get the following. And this is actually what gives us our rainbow inside of the robotics that we make. Okay, so that means this is great. We have the squishy part, we have the rainbow part. We can definitely build our robots now. Okay, but wait. There are a few problems, unfortunately, and it's actually not as easy as I or other people thought it might be from the beginning. For one, this robot is inherently soft and squishy, and there's no hard components inside the finger at all. And this tactile touch sensor is completely rigid except for this small piece of silicone at top. So there's not a really good way to actually combine these two without making a lot of sacrifices in between. But we want to use the best of both worlds. And another issue is that we have this camera here, which we need to find some space for so that it can actually have a clear view of whatever it's touching. Okay, so one of our first attempts, and one of the first things I tried to do was I tried to make a totally transparent, soft robotic finger. So here we have this funny triangle-looking shape. It's made out of transparent rubber and the flexible skeleton that's embedded inside that makes it completely clear. And the shape is actually based off of something called the fin ray effect, which is inspired by fish fins and how they can conform to things that are in contact with them. Then we put a camera embedded inside and we try to see through it. And it looks sort of cool. We can see through it. We can see what's happening. And you can actually see that when I run my finger along the side, it does this bending motion that I was talking about, which is really cool because if you put two together, you can try to grab things with this sort of bending motion without actually adding any sort of mechanical like motors. Okay, but here's the problem. You can actually see, if you look very closely, that this fin ray finger is running away from the contact, which means that if I try to grab anything, something will just fall out of it because it's actually too soft. It's too squishy, which I never thought was a possibility when I first started my PhD. And so this is only, unfortunately, one of many, many, many failed attempts. And I actually have a slide of a lot of different things that I tried. And I will have to admit, it's a secret between you guys and me that probably 90% of the things I tried didn't perfectly work the way I wanted it to. And it was a lot of struggle and repetition of experiments to try to get something that would actually work. And so after a lot of years of working on this and a lot of experimenting, I actually found two different strategies that ended up working out of all of these different strategies that I tried. First one is that we realized we have to use fluorescence. And the second one is that we could also use a flexible skeleton. So what exactly do I mean by that? And let's first talk a little bit about the fluorescence part of this. So why fluorescence? Well, let's take a look at our actual final fin ray finger design. Okay, so we have the skeleton on the outside so that it can do the compliance when we touch it. But actually, if we explode it out, we'll see that's a hollowed out structure. And that's so that we can put our camera in the back of it so that it can look at the silicone pad where the touch sensing will happen. But then we have an issue with where we need to put these LEDs or the lights, because as many of you guys probably know, LEDs are inherently rigid and they will interfere a lot with this sort of compliance structure. So I found a different way of doing that. So we take this silicone pad and we actually put this flexible piece of clear acrylic underneath it. And if we take a closer look at this flexible acrylic piece, we'll see that the sides are painted with green and red fluorescent paint. And this means that if you put a blue LED at the end of it, the blue LED can illuminate the entire length of this flexible piece, which causes, of course, the green and red fluorescent paint to, well, fluoresce. And so this means that actually, when we take a look through our camera, we see our tactile sensing. And not only is this, well, our rainbow with our red, green, and blue LEDs, we also see that we can see individual small details of anything we come in contact with because the camera is able to pick up that detail. Okay, so that's in a nutshell how the green or the fluorescence paint works. So now what about the flexible skeleton? The flexible skeleton is essentially this. So we use silicone rubber sort of like as like a skin. And this makes it so that if we grab or interact with a human hand, it's actually really safe and can't hurt the person who it's grabbing. But then we actually have a flexible skeleton on the inside to give it the added strength so it can hold something heavier like a drill, for instance. Then we take this sort of skeleton and we sneak our cameras inside of the skeleton because it's flexible but a little bit rigid so that I can actually house these cameras. And then we also can put LEDs embedded inside as well. This means that anything we make with a skeleton and with a silicone on top are both squishy, and the cameras allow us to see the touch. So this is actually a plastic strawberry that I'm rolling around on top of this skeleton and silicone. So we can actually even sneak cameras into the squishy fingers themselves and get continuous sensing along the entire surface, sort of like how our human fingers are. And when we combine all of this together, we can actually do things like what we like to call classify or recognize the objects that are grasped inside the hand. So you'll see here, we give it a Rubik's Cube and it's able to tell just from touch sensing that's holding a Rubik's Cube. And this is my favorite part. So we give this, I guess it's an orange toy cup, and we give it in this orientation. But then when we actually put it in a different grasp, the robot hand is still able to tell that it's a toy cup. So our overall hope is that we want to be able to take all of the work that we've done with these squishy rainbow robots, and we want to be able to hopefully use this technology to make even better robot prosthetic hands for people to use. And now, if you're like me and you think squishy robots are super cool, I have a few links for getting started. I do have to give you the caveat that you should do this with adult supervision so that because there's a lot of heating elements and also one of the tutorials requires actually having silicone rubber that you can mix together. But otherwise, all of these should be very simple to get started with if you're interested. And that's it from me. And I want to thank you guys all for coming here. And I hope that you guys are super interested in squishy rainbow robots as much as I am.
Thank you so much, Sandra. That was really, really cool. Thank you so much for showing us a little bit of the things, like the immense amount of things you've worked on. That was just totally tremendous. So I want to kick off our Q&A with a question to explain your background. Where are you in your background?
Sure. So I finished my PhD at the beginning of this year, actually. I'm currently working at a robotics company. And at the robotics company that I'm working at, I do a lot of hardware development, and I'm still building robotic hands. Believe it or not, I was actually very honored that the company took me because they were really interested in the robotic hands that I worked on at my PhD, and they wanted me to continue doing similar work.
That is totally awesome. So we have a question in the chat from a Northern Anglia student, Anandita, and Anandita is wondering, how could these new technologies that you've been working on help robots feel touch, like that robotic hand you showed at the end? How does that help prosthetics? Could this help them work more like real human hands and let people feel different textures and pressures?
Yeah, and that's a really perceptive question. That's the hope. The hope is that eventually, with these sort of touch sensors, we can integrate them into prosthetic robotic hands to actually help a person feel the things that they're missing out on. Because a lot of these robotic prosthetic hands don't actually have any sense of touch. And so, of course, this is really far in the future. So I haven't even started looking at this yet. But if we can potentially connect these sort of signals with the brain, then maybe we can mimic something that a lot of human hands can actually do.
That would be totally awesome. Now we have another question from Tom at North Anglia. And Tom's wondering, how much time did it take for you to make your first robot?
Oh my gosh. Well, that's a really great question. And I think so. It took maybe about a whole year for me to make my first ever robot. And although a year sounds sort of short in the long run, it was actually a very long part because if you think about it, that's 20% of my PhD spent on just building one robot. And of course, there were a lot more robots that I tried to build. But what happens is like after the first robot is built, a lot of things get easier and easier. So
That's good to know. And just to give some of the listeners context, how long does a PhD last? If you said 20% of your PhD was building that, how long is a PhD?
it depends for robotics. It can be anywhere between 5 to 7 years. I had to finish in 5 years because I think my advisor was like, okay, it's time for you to go. You've done a lot of good work. And I was actually very shocked when my advisor said that. I was like, really? You're not going to keep me for longer, like a lot of other people? So, um,
Got it. Okay. That is super good to know and super awesome. And yes, you have done an incredible amount of work, and it's just a pleasure to hear all about it. Now we have a question from Prahan, and Prahan's wondering, Sandra, why do you like to build squishy robots over rigid and hard robots?
yeah, that's a really sharp question. So the thing is, it's not that I don't like building hard robots. It's just that for some background in college, I was actually trying to build um, with, I guess, with my friends, a hand that could help assist people who have strokes and aren't able to move their hands anymore. So sort of an assistive device that can help them open and close their hands when they normally couldn't. And we originally actually wanted to build a rigid robot hand because we thought, oh, this is so cool. Like, why not? If we can do a rigid hand, we should go for it. But then as we started reading more and more about what other people were doing, we realized that actually soft, squishy robots were a lot better. So of course, I still want to incorporate rigid parts into the hands that I make, but to have the softness is to have this additional component of safety, which I think is really necessary if you want to interact with the world around you and with other people.
Absolutely. And that actually leads really nicely into a question from a Nord Anglia student named Kavya. And Kavya is wondering, have you used some of these squishy technologies to make robots that are available commercially? Are there examples of squishy robots we might be familiar with?
Yeah, and that's a really good point. So I think at least the work that I've done has not been made commercial. It's all, of course, on papers online, but I think there are other companies who have started to use more sort of squishy robots. So I guess one example is some medical companies are using this sort of squishy robotic worm, for lack of a better phrase, to sort of do exploration inside the human body so that they can do medical checkups and things like that. And other companies are actually using these squishy robots to try to make new robotic grippers that can be used in an industry sense.
Got it. Okay. And now we have a question from Nereus. And Nereus is wondering, can this sort of soft, squishy robotics, can you harness an artificial intelligence to help you build any of these things or come up with ideas of what to try? Have you been able to use that in your work or in your research currently?
Yeah, I really appreciate that question. So, I have not currently been able to use that in my research, but there's a lot of other cool researchers who are doing exactly that. So, one of the things that people are interested in is like, if you remember the fin ray one, that's the one that was inspired by the fish fin. A lot of researchers are saying, okay, so the fish fin is cool and everything, but maybe we can make it better using artificial intelligence to design something similar. We tell artificial intelligence, we want this fin ray that can actually do even more wild things. And then artificial intelligence creates these wild structures that I would have never even dreamed of.
Got it. Okay. And now we have a few questions about your background and getting into robotics in the first place. So we have a question from Ashray and Raja Vardhini who are wondering what made you want to get into robotics and make squishy robots in the first place. We have a question from Jace at BIS Boston who's wondering, did you participate in robotics in high school? I think they're just curious about your path.
Yeah, so actually, this is a very funny story. I was always interested in like just looking at robots, but I sort of looked at them from afar because I thought, oh, robots are really cool, but I'm probably too dumb to work on them because they look so awesome and they look so beautiful. And I'm just like some sort of like, small town person. And maybe I shouldn't work on this. I should let the actual like smart people work on this. But then, funny enough, one of my friends was really, really into robotics, and he kept on telling me, you should really try it. This is something you would enjoy. And I told my mom, and she was like, you should try it. I was like, that's sort of weird, but okay, I'll give it a try. So I went into the robotics club in my high school. So if I think first robotics competition, that's what I did a lot of. And I actually thought, okay, this is sort of cool, but this isn't like the robotics that I feel like I can make a career out of because I mean, I don't know who I'm helping. These are just robots that are, shooting basketballs and like kicking soccer balls, which is super fun. And I'm not saying it's not, it was super fun, but I was thinking, what about like things that can actually help? And it was during one of these competitions that there was this video that they played, and it was of someone called Henry Evans. He was a paraplegic, and which means that he cannot use his limbs at all. So he can't use his arms or his legs. And it was a video of a robot helping him brush his teeth. And I thought, that is so cool. There are robots that can actually help people. And that basically completely changed my worldview of robots. And so that's what really made me get into it. And I basically never looked back since.
Yeah, and sometimes, um, you know, working on fun problems like finding out how to make the robot, shoot hoops, is actually helpful and makes incremental progress towards making a robot that could help someone eat or move throughout the day. So that makes total sense. Thank you so much for walking us through that, Sandra. We have a question from Ishan now, and I'm thinking about the part of your presentation where you show your soft hand kind of gripping that Rubik's Cube and that cup. And Ishan's wondering, how does the robot know how heavy the object you're giving it is? Because if it applies too much pressure, Ishan's worried that the object will fall.
Hmm. Yeah, and that's a really, really great question. So I think one of the things that a lot of soft roboticists are able to take huge advantage of um, is that because we have this sort of built-in squishiness, or what we like calling compliance, when we grab an object, we can actually grab it with some amount of force. And because there's a squishiness, we actually don't worry as much about something falling out of the grass as if it were if the robot hand was made out of rigid components. And so I hope this answers the question, but essentially because of that, that means we can either grab objects with greater force, but where the squishiness envelops the object better, so there's more surface area to contact, and that makes it harder for this object to fall out.
Okay, got it. Okay, so there's a huge advantage to using that squishy material. More of that hand is in contact with that object, so it can't slip right out as easily. Got it. Okay, now we have a question from Kai, and Kai's bringing us back to prosthetics. Kai's wondering, in the context of prosthetics, what do you think is the compromise between having a prosthetic arm that's closer in texture, or firmer than a human arm, or a squishier arm? Could these sorts of technologies be used in surgery more than general use for an amputee?
Yeah, I think that's really perceptive. I think that's definitely possible. I think this is something that we're still all trying to explore in robotics. And honestly, I don't have the perfect answer for that. And I think that's part of what's fun about robotics. And maybe it's actually something that someone in this call might be able to do more research or do more work on and be able to one day tell me actually what's a good answer to that.
Okay, so we're still exploring this, and there's still just so much work to be done.
Actually.
You heard it here, Nord Anglia students. That's your next assignment. Okay, so now we have a question from Arena, and Arena is wondering, Arena says, thank you so much for this amazing presentation. For students aspiring to work and study in robotics and AI, what key skills and areas of study would you recommend focusing on? And did you enjoy studying robotics at MIT?
Yeah. Um, Okay, so that's a really interesting question. And I think part of the reason I also really like robotics is that robotics allows you to study a lot of different topics and still be able to get into robotics. So I know that there are some roboticists who are more into material science. So they study more about how materials work and how that can like integrate into that. Of course, mechanical engineering is a big part of it. You can use basically, if you learn how to design things or build things, that can help play a role. Some people, some roboticists, actually a lot of them now are computer scientists. So if you know how to program, that can also help you get into it. But there's just a lot of different ways to get into robotics. I personally think mechanical engineering is the coolest, but that's because I'm biased, because I actually really did enjoy my time at MIT studying robotics as a mechanical engineer.
Got it. Okay. Yeah, I love that it is integrated and it requires understanding a lot of different concepts from different fields. But you're right, mechanical engineering is an example of one field that does apply all of that information to, but there are multiple paths. Now I want to change over for a moment to talking about this rainbow concept. Could you walk us through why you use rainbows to help see? How does that work? Could you walk us through it?
Yeah, and I really appreciate you asking that. And so I think one of the things about the rainbow is that I guess for those who are unfamiliar with cameras, when you look at a camera image, a lot of times you can dissect it into three components. And those three components are the red color channel, the green color channel, and the blue color channel. And so what this is actually my advisor figured out was that if we can use those three color channels to our advantage, then we can get a lot of different things out. So although the rainbow looks really cool, the idea is because we have different direction of red, green, and blue lights, we can use the camera image, take one single image, and use the individual color channels of the camera to tease out information. And if we have that information, we can see basically how sharp a gradient is. So like, how does the green transition from like a lighter green to a darker green sort of? And then use that to actually get 3D information about the touch contact.
Got it. So essentially, this rainbow and these three colors, which when combined all together, make the color wheel and make that rainbow you're referring to. Essentially, this is just a way of helping see what the object is. It's not necessarily for fun colors. It is actually giving you specific information. Each of those colors is telling you something specific about that object. Is that right?
That's correct.
Okay. Got it. Thank you so much for clarifying it. I think we all got really excited about the rainbows and wanted to know more. Um, so people are wondering now, how many robots do you make in 1 year? Adia is wondering, are you still building robots currently?
Yeah, so during my PhD, at the beginning, I made my first robot over the course of a year. And then after that, let's see, I made 2 robots per year about. So a lot of different robots. But now that I'm working in a company, we're still in the process of building robots. And so I think we've been making a gripper. So we made one gripper in, I think, let's see, about 4 to 5 months. But also, I wasn't the only person working on that project. I think in my PhD, I was one of the only people in my lab working on this project, which probably was also why it took a bit longer. Yeah.
Got it. And now I'm wondering if we could talk, because we're talking about building robots. There are a few students in the chat who are wondering about perseverance. You referenced that, there was so many things that you had to try that didn't work. What motivates you to keep going with every setback? I think a lot of us are wondering, especially students who are interested in getting into robotics themselves.
And I'm really glad that this was asked. I think one of the things is it definitely helps to be really excited about what I was working on. But I think there were times when and I think this happens in a lot of people's careers and in their PhD, is that there are some times I would wake up, I would be like, oh my gosh, why am I doing this? I don't know if I'm the right person to do this. I don't know if I'm smart enough or good enough. But I think it really helped me to like be like, okay, chin up, it's okay. And to be surrounded by a lot of people who really loved and supported me. And I think one of my best friends in college, she would sometimes like tell me, she would be like, Sandra, you're so smart, you're doing great. You think everyone can go to MIT? I was like, okay, but like, there's a lot of people at MIT and I'm only one of them. And she was like, it's okay. I believe in you. And you know what? Once you make a lot of money doing robotics, let's just retire. We'll go to a tropical island and we'll retire together. And that really made me feel like really happy, and just like having so much support and love from other people was like really, really, really helpful.
Yeah. So the gist of it is, keep your chin up, take it day by day, but also lean on your supportive community and your friends and your loved ones. And they're more supportive than you may think in those hard times. Okay, so now we have a question from Arkash. And Arkash is wondering, how do you get ideas about robots? Do you like to go somewhere to think about new ideas or things to try?
Yeah, that's a really, really fun question. So I really like listening to music. So sometimes I just like listen to music and I'll just like, I can be anywhere, honestly. I can be anywhere and I'll just listen to music and then I'll just think about different things. So a lot of my inspiration comes from just like reading and thinking about different things that might be interesting. So like And also just like from also my advisor. So sometimes my advisor for the FinRay thing, he was actually the one who introduced me to FinRay. But for this sort of flexible skeleton thing, that was just for me just thinking, listening to music, and then I was looking at my hand. I went, what makes you so good? And what makes robotic hands so not as good? And it just sort of spiraled from there. So there's just a lot of inspiration everywhere. And it's just wherever you find the inspiration could be very valid.
So in some ways, it kind of can be surprising. It's unplanned. It just comes across. Got it. And now more questions about the robots that you worked on specifically. A couple of students are wondering, have you named your robots? How do you come up with what to call them?
Yeah. Oh, this is so fun. Okay, so unfortunately, I think in a lot of robotic fields, you have to make sure that the name actually works with what you're building. So even though I really like calling different robots by like different names, I also have to keep in mind that in a paper, whenever I write it or whenever I introduce the stuff I'm working on to other people, I have to give it like an official name. So for the Finrays, there's a big boy Finray, there's a baby Finray, but those are the secret names. The baby Finray is actually not a secret name because originally so it's just a really mini version of the Finray. Originally, it was going to be a secret name, and I was not going to put it on a paper. I called it version 2, but I had called it Baby Finray in lab so much that everyone said, "Oh, Sandra, you have to call it Baby Finray. We all know it as that." And like, it's okay. What's the worst that can happen? Like no one's going to reject your work just because you called it a Baby Finray. I went, okay. But then I thought big boy is probably too much. So that one's not, there's one that is not called big boy Finray, except for by myself.
Got it. Thank you for kind of pulling back the curtain and letting us learn about the behind the scenes names. That is really fun, but it also makes sense sometimes you have to give them names that are descriptive for the function, especially when you're sharing that with the research community and other people who build robots. So now we have a couple of questions from Nord Anglia students who are interested in the application. So they're thinking in the future on how to use these squishy robots. And they're wondering if you've ever thought about whether squishy robots could be helpful to explore the oceans, or could they ever be helpful to explore space?
Yeah, and that's a really wonderful question as well. So in a nutshell, yes. I think there's some, although I'm not sure, so don't quote me on this. I have heard rumors that I think NASA is looking into doing sort of soft robotic exploration in space because there are some environments that are really either like corrosive, so damaging to metal or other parts. So people are thinking, okay, maybe like something like softer material would not only be better at exploring things, it might be better at dealing with different environments. And of course, I don't remember if people remember the slide, but there was a slide where there was a robotic fish swimming around the ocean. So that was actually done to do some sort of ocean exploration as a project. And the reason being that fish were more okay with this soft fish because they were like, oh, it's just a soft fish. Like it's not this weird like metal hunk of a fish swimming in the ocean and sort of scaring people. It's sort of like how like for humans, I think if I saw a big metal robot coming at me, I'd probably run the opposite direction. Um, but if it was like something like Baymax, like I would be like, oh, hello, Baymax. So.
I would also run in the opposite direction. Okay, we have a question from Nico at BIS Boston, and Nico's wondering, what's the funniest mistake you made when you were building one of your robots? Can you recall an amusing moment?
Yeah, there are so many funny things that happen. And I think because I was working so late in the night, I definitely have made a lot of funny mistakes. So I think one of the things that happened was so a lot of squishy robots requires you to mix and then pour this silicone rubber. And so I was really tired. I was so done pouring silicone for my robot hand. I thought, if this doesn't work, maybe I should just take a vacation or something. Of course, I was not going to, but I was like really considering it. And so I just poured it in. I went, okay, it's fine. It's like really late at night. I'm going to go home. I'm going to take a mental break. And then I came back the next morning and there was no silicone inside of where I had poured it. I went, what happened? And then I looked and I had forgotten to tape one of the holes up. And so it just leaked all out of the side. There was a huge puddle on the on our wet lab desk. And I went, oh shoot, I have to clean this up before everyone finds out that I did this. Yeah, and there's just like a lot of other things like I think sometimes when I'm writing about my stuff, so sort of like documenting all of my research, I'll write really funny things. I think one of my friends made fun of this like sentence that I wrote in one of my papers, which was I wrote, the camera can see colors, and I left it there in my paper and I sent it to review and everyone laughed at me.
It sounds like you have a good group of people around you, though. That's really nice. And thank you so much for sharing that silicone story with us. I know that, yeah, sometimes building things and working on the sort of stuff we work on can be really challenging and takes us late at night. So we make little mistakes, but it's all okay and we get past them.
For sure.
Sandra, we unfortunately don't have any more time for questions, but I wanted to thank you for sharing all of these amazing insights with us. And I'm really excited for students to pursue those links and those QR codes that you posted in your slides. And that leads me to remind our Nord Anglia students and community on the call that you can also find recordings of our past abstracts if you want to reference those. Now, before we go, I wanted to show you all our coming abstracts. Next time, we're really excited to welcome Jared Rivera, who's going to tell us all about the Northern Lights. And before we all say goodbye, I'd like to thank everyone for joining us today. Thank you to all the students for asking such wonderful questions. And thank you to the MIT Nord Anglia Education Collaboration for making this series possible. And thank you again very much, Sandra, for sharing your research and insights and experiences with us all today. Thank you so much. Okay, see you all next time. Goodbye.